Hey folks, back again. Here we are on problem number 6, and it's looking like we're going to be doing some derivatives here to find a Maclaurin series. So why don't we just go ahead and get at that. It wants us to build, it looks like a third degree Maclaurin series for f of x. So let's start with f of x. Suppose I got to turn the marker on. F of x is equal to e to the x sine x. Since this is Maclaurin, I will evaluate that at 0. And e to the 0 is 1, and sine of 0 is 0, so that'll be 0. Okay, let's find f prime. I have a feeling I'm going to need some space here. That's going to be product rule. Oh, glitchy. I don't know what's going on there. Product rule, so that'll be derivative of the first times the second, plus the derivative of the second times the first. Okay. That derivative evaluated at 0. The first term will still be 0. The second term will be 1. Okay, I'm going to do the second derivative up here. So it's going to be the first derivative, okay, and the reason, part of it will be the first derivative, because if I take the derivative of this thing, okay, I get the same thing as the first derivative, so it'd be e to the x sine x plus e to the x cosine x. And then I'm going to take the derivative of this using the product rule. And I get e to the x cosine x minus e to the x sine x. So what you'll see here is that this first term and the last term there are going to reduce. So the second derivative kind of folds on itself, giving us 2 e to the x cosine x. So the second derivative evaluated at 0 will be 2. Okay, in a similar fashion, it wants us to go up to a third degree Maclaurin, so I'll have to do the third derivative. In a similar fashion, I've already done the work on the side. This will come out to be 2 e to the x cosine x. With a similar collapsing type, not collapsing sum, but a similarly collapsing behavior, and we'll get that for our third derivative. Okay, therefore, e to the x sine of x, written as a Maclaurin polynomial, will be x, right? No constant term, right? Because f of 0 is 0. So I have x plus 2x squared over 2 factorial plus 2x cubed over 3 factorial. Let's just real quick highlight. That's where my 1 comes into play. That's where my 2 comes into play. That's where my other 2 comes into play. And if you decided to simplify, you get x plus x squared. Oops, I forgot a factorial down there. Plus x cubed over 3. All right, so there you have it. 7 marks. I would say that's a very, very accessible 7 marks, which gets you on your way to passing the exam. All right, 6b, it says hence would mean using part A, or otherwise, in this case, otherwise using L'Hopital's rule, which in this case you'd have to use a number of times. So I would not suggest otherwise. I would suggest using what we've already built for ourselves. Let's replace e to the x sine x with this polynomial. All right, and let's see what happens. So the limit as x approaches 0. Clearly, I mean, if I plugged a 0 in for every x, I will get 0 for in my yellow box. I will get 0, I will get 0, and I'll get 0. So clearly that would be a candidate for L'Hopital's rule if we decided we wanted to go there with it. I would not advise that. That would be a poor choice, not wise. Lots of work. Because look at how nicely they've built this for you. Okay, now I really should. I guess I didn't need to do that. Let me do this. I really should say that this expression goes on, and it will have a 4th degree term and a 5th degree term, and etc. But I'm only going to use the first 3 terms, and you'll see why in just a second. All right, so if I take this expression, I can simplify out this x with that one, x squared with x squared, and then I'm left with the limit as x approaches 0 of x cubed over 3 plus, I don't really care, let's say ax to the 4th over 4 factorial. I don't know what that is. On down the line, right? It's all this extra stuff that I'm writing right now is not necessary. By extra, I mean this. That's not necessary. Okay, you can already see that the answer is going to be 1/3. But what will happen is as I reduce out x cubed, that makes that ax over 4 factorial, which as x goes to 0, that will end up going to 0 anyways. Right, and so will the next term, and so will the next term, etc., all the way down the polynomial. Therefore, I'm taking the limit as x goes to 0 of 1/3, which, like, if I mess that one up, I got some issues. But it looks like my limit comes out to be 1/3. They set these up intentionally for you to collapse them down to something very simple and, again, accessible. So please take advantage of that. All right, for some reason this got split here, but 6C is also 7 marks. So this one altogether is 17 marks. It looks like we're going to use a Lagrange here on 6C. As we jump into it, let's remind ourselves how to do a Lagrange error. This is not frequently seen, but it's okay. So the error of the sum of the first n terms is going to be less than the absolute value of the n plus 1th derivative evaluated at some value z. That derivative we want to maximize, so we want to maximize the n plus 1th derivative by testing 2 possible values. Oops, I shouldn't have 4's there. I should have n plus 1's over n plus 1 factorial. Okay, I want to maximize, not z, but I want to maximize the n plus 1th derivative evaluated at z by testing one of 2 things. Test the center and the value at which you're approximating. I'm going to spell it wrong, so just deal with it. Okay. So, for example, in this situation, we have a Maclaurin series. So my center, because it's Maclaurin, would be x equals 0. And my value that I'm approximating would be at x equals 0.5. Okay, so for this situation, use the Lagrange form of the error to find an upper bound for the absolute value of the error in this approximation. All right, so I've got a third degree Taylor, so I would want, or excuse me, Maclaurin, so I would want error of the first three terms, which will be less than the fourth derivative, evaluated at either x equals 0 or x equals 0.5 times x, which in this case will be the center, okay, to the fourth power over 4 factorial. So this is important too. I didn't mention this. This x value will be the approximation value. Okay, so it will be that 0.5. That won't change, right? But the z value we're going to test at x equals 0 and at x equals 0.5 and determine which one is larger. So in this case, the fourth derivative ends up being, and I did this work on the side, right? We did all that work with e to the x sine x earlier. That's our fourth derivative. So if I took the absolute value of the fourth derivative evaluated at 0, I would get 0, right? Because sine of 0 is 0. If I took the absolute value of the fourth derivative at 0.5, I would get negative 4e to the 0.5 sine of 0.5. That value will exist, okay? And therefore, it has to be, right? It has to be larger than 0. So we're going to use, in this case, the approximation value of 0.5 because it will maximize the error. Okay, so this right here, this value is whatever that is, okay? And then we're going to multiply it by 0.5 to the fourth, and then divide that by 4 factorial. So using my calculator, of course, don't forget absolute value, I end up getting 0.00823. So if it asks for sig figs, 3 sig figs actually would be that, right? We would use those last 2 and 3 as our second and third sig fig. Okay, so that's part 1. Part 2 asks, deduce from the Lagrange error whether the approximation will be greater or less than the actual. Okay, so based on the error, if your n plus 1th derivative maximized, whatever z value you use before the absolute value is less than 0, then it will be the actual value, the approximated value. So how do I want to note that? How about approximate will be less than the actual. So in this case, that would be true, right? Because I believe this comes out to be a negative number. Whatever this thing is, I don't know what it was exactly, but it's less than 0. And the flip is also true. So if that thing ends up, whatever you end up using ends up being greater than 0 prior to using the absolute value, then the approximation will be greater than the actual. So in this case, that's what we got. This is a tough one. Lagrange doesn't come up often, but be familiar with this form, right? Our general form, and honestly, just if you put that down on paper, you might get 1 or 2 marks. So, all right, that's it for this one. We'll see you on the next.